An artificial neural network, or ANN, is a powerful supervised learning algorithm designed to analyze data in a way that's reminiscent of how our own. An artificial neural network, or ANN, is a powerful supervised learning algorithm designed to analyze data in a way that's reminiscent of how our own brains operate. As we dive deeper into this fascinating realm of technology, we'll explore its fundamentals, we'll look into how it functions, and what's super exciting is how you can implement your very own ANN using Python. So let's get started, shall we? Understanding the structure and workings of an ANN can open up a whole new world of possibilities in data analysis and machine learning. You'll see that the principles are not only intuitive, but also incredibly powerful when applied correctly. So, are you ready to unlock the secrets of this transformative technology? Let's go. To grasp the essence of neural networks, it's essential to understand the architecture of an artificial neural network, or ANN. At its core, an ANN consists of interconnected nodes, or neurons, organized into layers: the input layer, hidden layers, and the output layer. When data is fed into the network, it flows through these layers, allowing the network to learn complex patterns, much like how our brain processes information. An ANN adjusts the weights of its connections based on the input it receives. This adjustment is guided by a process known as backpropagation, which fine-tunes the network's performance over time. Now, to illustrate this concept, let's imagine developing an ANN that recognizes handwritten digits from 0 to 9. The input layer of our network accepts pixel values from images of the digits, while the output layer consists of 10 neurons, each corresponding to a digit. As the ANN trains on these images, it learns to associate specific patterns of pixel values with their corresponding digit. Isn't that fascinating? We're essentially teaching a machine to interpret visual information just like we do. Now, let's implement the necessary steps to prepare our environment and the dataset for our digit recognition task. First, we need to make sure TensorFlow is installed in our Python environment. This is super important because TensorFlow provides the tools we need to build and train our neural network, and we install it using pip, the package manager for Python. Now, once TensorFlow is up and running, we'll import TensorFlow itself, along with some Keras modules that help simplify the process of building those neural networks. Specifically, we'll bring in layers and modules, which will help us create the structure of our artificial neural network. Plus, we can't forget about the MNIST dataset, which contains images of handwritten digits and is conveniently split into training and testing sets. So after we've got all the necessary libraries imported, it's time to load up the MNIST dataset. This will give us the training and testing data we need. Now, it's crucial that we normalize the pixel values of these images to a range between 0 and 1. Why, you ask? Well, normalizing helps improve the efficiency of our model during training and allows it to converge faster, which is vital for effective learning. By converting our data to float32 and dividing by 255.0, we're ensuring that those values are in an optimal format for processing. Next, we're going to construct the architecture of our artificial neural network, or ANN, specifically designed for digit classification. So let's jump right in with a sequential model using the TensorFlow Keras API. The first layer we're going to implement is a flatten layer. This layer is crucial because it transforms our input images, which are in a 2D format of 28 by 28 pixels, into a 1D vector of 784 elements. This step is super important as it allows the data to be seamlessly processed by the layers that follow. Now, after we've added the flatten layer, we proceed with a dense layer that has 128 neurons, and we're going to employ the ReLU activation function here. This hidden layer is where our ANN really starts to learn to identify complex patterns and features within those digit images. The ReLU function introduces nonlinearity, which is key, allowing our model to capture intricate relationships between the inputs and outputs. Finally, we'll include another dense layer, but this one will consist of 10 neurons and utilize the softmax activation function. This output layer will generate a probability distribution across the 10 classes, representing the digits from 0 to 9. By implementing this architecture,
architecture, we're laying down a solid foundation for training our ANN on the MNest handwritten digits dataset.
Next, we will compile our model to prepare it for training. This step is super crucial because it involves defining the optimizer, the loss function, and the metrics we'll use to evaluate the model's performance. In our case, we're going with the Atom optimizer. It's known for its efficiency in handling those tricky gradient updates. Now, the loss function we've chosen is sparse categorical cross-entropy, which is really well suited for multi-class classification problems where our labels are integers. Finally, we'll specify accuracy as our evaluation metric, which will let us keep an eye on how well the model is doing during training. Now, let's dive into training the model with our dataset. We'll be using the fit function, which in a nutshell will adjust the weights of our network based on the input data over a specified number of epochs. By setting the batch size to 32, we control the number of samples processed in each iteration, leading to manageable updates to the model's weights. Less noise is always a good thing in this process. Running for 5 epochs will give us some insights into how well the model is learning. While we do this, it's important to carefully observe the output, as it can provide valuable feedback on its learning trajectory. Now, let's evaluate how well our trained ANN model performs on unseen data by using the evaluate function. This step is crucial, as it helps us ensure that our model generalizes well and hasn't just memorized the training data. When we call the evaluate method with our test dataset, it computes the loss and accuracy, allowing us to understand our model's effectiveness on previously unseen samples. The results will be output, giving us the test accuracy formatted to 4 decimal places. Next, to visualize the model's performance, we can plot some predictions alongside their actual labels. This not only helps in assessing how well the network predicts digits, but also provides an intuitive understanding of its decision-making process. We'll begin by importing the matplot library for plotting, and then obtain predictions for the first 10 images from our test dataset. By using tf.argmax, we can extract the predicted labels for these images based on the model's output. Finally, we create a visually appealing display where each subplot shows an image along with the model's predicted label, making it clear how accurately the ANN recognizes the handwritten digits. The displayed figure is a line chart titled Classification Error Rate in ImageNet over the years, and it visualizes some really interesting data. On the x-axis, we have the years, from 2010 to 2016, and on the y-axis, we see the error rate, represented in percentages. Now, let's dive into the plotted values. Starting with 2010, we see an error rate of 28.2%. It then goes down to 25.8% in 2011, which isn't much of a dip, but hold on. Things get exciting in 2012, where the rate drops dramatically to 6.7%. That's a whopping decrease of 19.1 percentage points, making it the most significant change in this entire period. After that, from 2012 to 2013, we see a smaller decrease of just 1.6 points. Then it goes down by 1.5 points from 2013 to 2014, by 0.4 from 2014 to 2015, and finally just 0.1 points from 2015 to 2016. So, while the overall trend is a strong downward trajectory across these years, moving from 28.2% in 2010 to just 3.1% in 2016, a total reduction of 25.1 percentage points, you can notice that the pace of improvement really slows down after that initial leap. The markers on this line chart highlight each annual measurement, and the dashed grid lines help us read those exact values and make comparisons between years a lot easier. So, what can we conclude from this chart? Well, the most dramatic improvements seem to happen in those first couple of years, while later years show these diminishing returns when it comes to further reducing the classification error. Fascinating stuff, right?
Next, we're going to delve into a crucial aspect of training our neural network, weight adjustment using the backpropagation algorithm. The line of code we'll write will show how we tweak the weights based on computed gradients. Specifically, we're going to subtract the product of the learning rate and the gradient from the current weights. This means we're effectively making a step that should bring us closer to reducing the error in our predictions. Now, the term learning rate is really important here. It determines how big that update step is. If we go with a smaller learning rate, we make more gradual changes, which can help us fine-tune our model. But keep in mind, it might also increase our training time. On the flip side, a larger learning rate can speed things up, but runs the risk of overshooting optimal weight settings, which could lead to divergence and instability. So this line is a fundamental building block for training our artificial neural network. It encapsulates the essential process of weight optimization, and getting this right will empower you to understand how neural networks improve their predictive ability over time through repeated exposure to training data and careful parameter refinement.
Now let's implement a basic convolutional neural network, or CNN architecture, for our digit recognition model. And don't worry, it's going to be quite manageable. We'll kick this off by using the models.sequential class, which is perfect for building our model layer by layer. The very first layer is a conv2D layer that has 32 filters, with each filter sized at 3 by 3. This layer is super important because it applies convolution operations to extract essential features from our input images. And we'll use the ReLU activation function here to introduce some nonlinearity, which helps in learning complex patterns. Next up, we'll add a max pooling 2D layer with a pool size of 2 by 2. This pooling layer is great because it reduces the spatial dimensions of our feature maps, focusing the model on the most significant features while cutting down on any unnecessary noise. Following that, we add a second conv2D layer with 64 filters. This layer really digs in, refining those extracted features by applying even more convolutions. Then we have another max pooling 2D layer that further downsamples our feature maps. It's like giving our model a clearer view. After that, we encounter the flatten layer, which is crucial as it converts our 2D feature maps into a 1D vector. This flattened output then flows into a fully connected dense layer with 128 neurons, also using the ReLU activation. Finally, we cap it off with another dense layer, featuring 10 neurons and a softmax activation function. This setup provides output probabilities for each digit class from 0 to 9, and the best part? This architecture is crafted to significantly boost our image classification performance.
After adjusting our model to a CNN, don't forget to compile and train it just like we did before. You can expect better performance from this elegant approach the CNN leverages for image data. Also, remember to keep track of your accuracy after each epoch. I know, it's easy to get caught up in the excitement, but monitoring those performance metrics is so important for understanding how well your model is really learning. Now, while we've covered a lot, the frameworks and techniques available for developing ANNs are quite extensive. Techniques like regularization, dropout layers, and data augmentation, they can all help us boost model performance and combat that pesky overfitting. You know, that's when a model learns too much from the training data and then performs poorly on unseen data. So keep these techniques in your toolkit as we work to enhance our models together.
In summary, artificial neural networks, or ANNs, represent a fascinating intersection of biology and technology, enabling significant advancements in fields ranging from image recognition to natural language processing. By understanding the fundamental components of ANNs, one can leverage their power to solve intricate problems in various domains. Now, you've been introduced to the basics of building an ANN using Python and TensorFlow, along with some key techniques for improving model performance. Remember, as you dive deeper into machine learning, don't hesitate to experiment with different architectures, optimizers, and hyperparameters. The world of neural networks is vast, and creativity is your best ally in this exciting journey.